is this corollary. The Wasserstein distance will be upper bounded by this expression where R is eliminated. And it is tight whenever PZN is isotropic Gaussian as before. And the natural exercise to do, of course, would be to compare this right-hand side to the right-hand side of Talagrand inequality, right? Which is 2 times the KL divergence between PZN and PYN, right? It turns out that this right-hand side is indeed always tighter than, in general, tighter than 2 times KL divergence. In other words, this inequality indeed sharpens Talagrand one for any PZN. And also the inequality itself is tighter for a wide class of PZN, as we just mentioned. And interestingly, it turns out that this inequality indeed appeared actually not, not very old result. It actually appeared previously in the 2012 result by Bakri et al. And now it's basically included as a corollary of our, information constrained transportation equality. And what is perhaps more interesting, in my opinion, is not the instantialization of R to positive infinity. What is perhaps even more interesting is that if you think about this inequality in the information constraint sense, right, it goes beyond of Talagrand transportation equality, in the sense that it characterizes a trade-off between the information constraint and the upper bound on the Wasserstein distance, right? And as we just shown, when R gets to positive infinity, the upper bound reduces to the sharpened transportation equality, right? Which sharpens the Talagrand right-hand side, right? And the other extreme is when R becomes 0. So what does it mean when R becomes 0? It means that the mutant information is 0, which further implies that Zn and Yn are completely independent to each other, right? So this is a sufficient and necessary condition for mutant information to be 0. And therefore, in that case, the Wasserstein distance between those two probability measures simply reduces to the sum of the respective second moments of Zn and Yn, right? Because they are completely independent. So the sum would be second moment of Zn plus Y plus N, because Yn is standard Gaussian. Within, for any R which is between 0 and positive infinity, our inequality actually characterizes a trade-off between the information constraint and the Wasserstein distance. So, demonstrated by this curve. And again, this trade-off is indeed tight when PZN is isotropic Gaussian. So what is the implication of, what can we learn about this trade-off, right? So maybe different people have different view on it. From our perspective, and we are actually currently exploring the application of this result. We are actively exploring the application of this result and this formulation and this distance to the machine learning domain. But in the current talk, let's just focus on some information theoretical related problems and the results. So the first application would be to the domain of concentration of measure, which actually has a lot of applications, even in machine learning, in statistical learning, right? Because concentration inequalities will be extensively used for bounding the sample complexity, especially in the pack learning framework. So,
I have a question.
Yes.
The bound on the. So, I don't know if it makes sense, but like I see, it just depends on Z of n. Doesn't depend on Y of n, your original space?
Oh, yes, because I already specified PYN to be standard Gaussian. So PYN is already fixed. That's a good question. But in Talagrand one, PYN is fixed as well. In general, if PYN is not fixed, if you want to upper bound the distance, right? So that could be a non-trivial task. As far as I know, if I interpret correctly, right? So one of the key contributions of Villali, right? So who was invited to our ISIT plenary talk a few years ago, I guess, in Munich or in Barcelona, I can't remember exactly. So one of his contributions, right? would be to show, to upper bound this Wasserstein distance for a wider class of PYN. For example, when PYN is log concave instead of being standard Gaussian. Okay, but that's a good question. So, but it turns out that, connecting to your question, the measure concentration of concentration measure result in the Gaussian space can be obtained as long as PYN is restricted to Gaussian. In other words, for the purpose of deriving concentration measure result, it suffices to assume PYN to be standard Gaussian. Okay, so and in particular, right? So we have mentioned that the Talagrand transportation inequality can be used to derive concentration measure in the Gaussian space, and this was pioneered by information theorist Carl Marton in 1980s. And in particular, what we can show by using this transportation inequality is the following so-called blown up lemma. Okay, I realize maybe not all of you have heard of this lemma, so let me explain it very briefly. So what this lemma says is the following. Imagine you are in the Gaussian space now. Gaussian space means, the measure, the n-dimensional Euclidean space equipped with the n-dimensional standard Gaussian measure. So just imagine your basic measure, think of volume, not in terms of the bag measure, but in terms of Gaussian measure, right? So in this probability space, suppose you start with some, let's say, small set, right? Small in terms of its probability measure. If the set has probability measure E2 minus n small a, right? If you blew up this blue set with a small yet carefully chosen radius, in this case, it's square root of 2 times NA, right? So this A is identical to this A in the exponent. If you blow up it with a small yet carefully chosen radius like this, then the resulting set will have probability roughly 1. In other words, in the high dimensional space, right, the probability is concentrated around a small set. The small means volume, right? So, or measure. So around a small set, right? So that's what we call, that's how the name blown up lemma arises, hence the name blown up lemma, and as well as the concentration measure, right? So, interestingly, I guess maybe not all of you have heard of this blown up lemma, but I'm sure, right? So most of you have, either have used or at least encountered the so-called functional version of the measure concentration results, right? For example, in the Gaussian space, the functional version of concentration measure says that if Yn is standard Gaussian, for any Lipschitz continuous function f, the function value will be concentrated around its expectation. Okay, so that's a functional version. Although those two, I know it appear rather, there's dichotomy between those two, results, but it turns out that they are indeed equivalent to each other, and it can be used to derive each other. Actually, through a couple of lines, it's not even, very complicated exercise. Okay, another comment I want to mention here is that one way to think of the blown up lemma is through the angle of isoperimetric inequality, right? So the isoperimetric inequality actually has been known, maybe 100 years ago by those ancient Greeks, right? In a two-dimensional plane, it simply says that among all the sets with the same, area, circle has the smallest neighborhood or smallest extension, right? And it turns out that to prove the blown up lemma, one way to derive it, or the fundamental way to view the blown up lemma, is the following. Because I start with a small set of the given measure, right? It suffices for me to work out what is the worst case, of the shape of this set if I want to blow up the regional set with some radius. It turns out that in the Gaussian space, the worst case, right? Previous I showed that, everybody knows that in the two-dimensional plane, the worst case is basically a circle, right? And in a three-dimensional space, the worst case is a sphere. In the Gaussian space, the worst case turns out to be a half space, right? Just like this. It turns out that as long as you bring this half space across the orange to include, basically across this orange, then it's easier exercise to show that the resulting set will have probability roughly 1. And therefore, the blown up lemma can be thought of as, basically a corollary of this isochronicity phenomenon. And in that sense, what does the Talagrand transportation inequality mean? What does that do is to capture this worst case characterization through a probabilistic language. Okay, so this is a key point. And this key point will also carry over to our new concentration measure phenomenon. Basically, we show that, so this is our new connection. We show that using the sharpened transportation inequality without rate constraint so far, but the sharpened version will actually imply the blown up lemma on the sphere instead of in the Gaussian space. And note that now the blown up lemma is on the sphere precisely because instead of controlling KR divergence, now you're controlling what? You're controlling the second moment of Zn, which translates to the radius. Imagine Zn is living on this sphere, right? The radius of this sphere corresponds to the second moment of Zn, and the entropy of Zn, right? Through the, information theoretic, connection between entropy and the volume of its typical set, right? So entropy governs the volume of its typical set. So this entropy translates to the volume or the measure on this sphere, right? So basically those two allows you to control the regional measure of a subset. And the blown up lemma says that if the regional subset is of a certain measure, for example, if you collapse that into like a cap-shaped subset that is of angle theta, it turns out that using this transportation inequality, you can show that whenever you blow up the regional set, gray area, by a blown up angle instead of blow up radius, blow up an angle omega, which is 2 pi over 2 minus theta, then the resulting blown up set will have probability roughly 1. In the similar fashion in the blown up lemma as the blown up lemma in the Gaussian space, but now on the sphere. And then, it's also well-known phenomenon is also well-known fact that this is actually stronger than blown up lemma in the Gaussian space, simply via implies at least, maybe they are equivalent in some sense, but at least this implies the blown up lemma in the Gaussian space via change of coordinate from the sphere to an Euclidean dimensional space. Okay, so and this, this implication is from the sphere to the Gaussian space should not be surprising at all, because if you think about the transportation inequality world, right, this sharpened version is indeed, stronger than the one in the Gaussian space in Talagrand transportation inequality, actually. Okay, perhaps even more interestingly, it turns out that, this new transportation inequality with the rate constraint, with the mutual information constraint, leads to a new concentration result on the sphere. And then let me explain to you what is a new concentration result. Oh, by the way, the original blown up lemma on the sphere can be really thought of as characterizing spherical cap as a worst case, right? Because the omega pi over 2 minus theta is enough to blow up the cap to contain the half sphere, which has probability roughly 1. And the sharpened transportation inequality can be thought of as capturing basically the worst case shape of on the sphere to have worst case in the sense that has minimal volume of the blown up set. And what is the new concentration result says is the following: given a subset of certain measure, if you random pick a point on the sphere, say Yn, and draw a ball around this Yn, look at the intersection measure between the original subset and the ball around the Yn, we can show that this intersection measure can be tightly bounded, tightly lower bounded in high dimensions as dimension goes to infinity, basically. And why we have the tight lower bound intersection measure? That all because now we have restrict the mutual information to less than R, because equivalently you are lower bounding the conditional entropy of Zn given Yn to some constant number, right? And the lower bound on the conditional entropy will translate to a lower bound on the intersection measure. Why? Because again, conditional entropy measures or governs the volume of the conditional typical set. Think about this intersection measure as the conditional typical set given Yn, and therefore we can derive this new concentration result from our information constraint transportation inequality. Okay, so I probably skip this comparison. How much time do we have? Like we'll stop at 2 o'clock or?
Yeah, so around 2, so maybe around 10 minutes. How much time do you need?
Maybe just 10 or 15 minutes. I'll briefly show application of it.
That's fine. Yes, good.
Okay, so I'll probably skip this, but just one sentence, mentioning would be the new concentration result indeed includes the classical blown up lemma on the sphere as further a special case, in the sense that when omega, the intersection, in the sense that we capture intersection measure, and the classical result basically says that intersection measure will be non-negative, while we provide, this transportation inequality provides a sharp lower bound on the intersection measure. Okay, with all this, we actually have a complete view about the interplay between transportation and concentration depicted by this diagram, where the existing work are colored in blue and the new findings are colored in red. Right? So the first, at the top layer of this diagram would be Talagrand transportation inequality implying measure concentration in the Gaussian space, and this connection was first noted by Marton. At the middle of the layer of this diagram is sharpened transportation inequality and measure concentration classical blown up lemma on a sphere, right? And we show that there's indeed a connection there. And finally, at the bottom of this layer, we show that our new information constraint transportation inequality implies a new result, concentration result on sphere regarding the intersection measure, which respectively include the previous inequality and the concentration result as special cases. Okay, so finally, I would like to briefly discuss using the last 10 or 15 minutes about one application of the transportation inequality to network information theory. And basically, turns out that it can be used to to resolve a long-standing open problem posed by Cover, actually collected into this this book titled Open Problems in Communication and Computation. And actually in this book, one of the open problems posed by Cover is called the capacity of the Rayleigh channel. And as you can see, the formulation is actually extremely simple, not even exceeding 1 page. So let me maybe explain this problem setup using one slide here. So the problem we consider is a so-called Gaussian Rayleigh channel, where imagine M is your message, you encode your message into n-dimensional code word xn, right? And send this xn through a Gaussian Rayleigh channel, where xn now is corrupted by two independent Gaussian IID noises, W1n and W2n, and the corrupted version, Zn and Yn, are received by, this is a Rayleigh node, received by the Rayleigh Zn and the destination Yn, right? And we assume the relay can communicate to the destination via some digital link or bit pipes of capacity C0. Okay, so the problem is basically to find out what is the capacity of the whole system, of the Rayleigh channel as a whole system in terms of C0, right? So this is a simple question, well defined. It turns out that determining the capacity in several extreme cases is actually quite simple. For example, when C0 equals 0, right? That basically means that this channel link is gone, and the Rayleigh channel reduces to a point-to-point channel from X to Y, whose capacity is given by the well-known Shannon formula. On the other hand, if C0 equals positive infinity, right? Which means that now you can do the joint decoding based on Zn and Yn together, because relay can losslessly transfer its observation to the destination, right? So the channel reduces to another point-to-point channel, but now with single input, but two outputs, Zn and Yn together, right? Whose capacity, again, can be easily characterized. Now, given those two extremes, Cover's question is to ask, what is the minimum needed relay to destination communication rate so that, let's denote that by C0 star, so that the capacity of C0 star can be made as large as the full capacity, meaning that, as if you are, as if Zn and Yn are achieving fully cooperating in decoding message of Xn. So what is the minimum needed C0 star? And so a couple of years ago, together with when I was a postdoc at Stanford, together with lab mate Barnes and Oscar, we showed that this C0 star is indeed equal to positive infinity, which means that in order to achieve the full capacity, the relay has to losslessly transfer its observation to the destination. There's no smarter way for the relay to do some, there's no freedom for him to, to do some, smarter strategies than simply basically transferring losslessly of its observation to the destination. So in terms of proof, the proof at that time when we work out this solution is heavily building on a geometric argument, which relies on the new concentration result on the sphere we have just shown. But at that time, we actually do not know the connection between, there's not even information constraint to transportation inequality, let alone the derivation from there to this geometric result. So what we do at that time is to invoke a pure geometric rearrangement theory and characterize this intersection measure, lower bound of this intersection measure. And on the other hand, what we have to do at that time, on the other hand, would be to lift the random variables from the n-dimensional space to a higher dimensional space, so that, let's say, nb dimensional space, so that this, the concepts or notions of typicality will arise, and therefore connect entropy, right? Connect the entropy in the n-dimensional space to the volume in the higher dimensional space. But now with the new approach, right, with the new transportation inequality with information constraint, what we can do is to directly work with the n-dimensional random variables without explicitly going to this nb dimensional space, or without explicitly looking at intersection measure. And we can directly work with the n-dimensional, random variables via the functional way, or the traditional information theoretic language, at least different approach, but the same language. And it turns out that we can recover our previous result just to a couple of lines, a few lines, maybe not exceeding half page. So I'm not going to the details of the proof because the time constraint, but just want to spend maybe 1 minute before we conclude this talk, spend 1 minute about the new insights on this new proof technique. Okay, so it turns out that our, this result really follows from a new upper bound on the capacity of this relay channel, and how to bound the capacity of the multi-user channel in general, right? So in general, what you do, for example, in the Gaussian relay case, what you do is that you start with the Fanon's inequality, which is a standard starting point, and then you use the data processing inequality, right? Because UN, suppose UN is relay's transmission to the destination, right? Because UN is some function of Zn subject to function f, right? So you use up data processing inequality to upper bound this, compression, to upper bound this, right? So expression by this expression, right? And then you follow from this, you get the so-called broadcast bound in the cassette bound. So what we do alternatively, or maybe a new approach to get a tighter bound, which allows us to solve converse problem, is actually to introduce an auxiliary random variable z bar n. But note that this auxiliary random variable is largely different from the typical auxiliary random variable which you encountered in the standard network information theory arguments. The difference is that in the standard network information theoretical derivation, right, you start from this expression and you kind of singularize that, and eventually you passively arrive at some, maybe complicated expression, and you passively let those, set of random variables to be some auxiliary random variable. For example, in the derivation of the converse of a Gaussian relay channel, right? So discrete memory is a broadcast channel, sorry, given by Gallagher. And also that approach is widely known as a Gallagher approach, Gallagher bound, Gallagher converse. The difference is that here we proactively construct a Z bar n. And the basic the philosophy is that I want to construct this Z bar n, which facilitates our subsequent upper bounding of the capacity. And why it facilitates? Because now we can utilize the transportation inequality. Originally this is a random variable Zn and Yn. Now using transportation inequality, what we can show is that we can find a different coupling of Z bar n and Yn. So the joint distribution of Z bar n and Yn will be different. In particular, given Xn, previously given Xn, Zn and Yn are independent, but now given Xn, Z bar n and Yn are correlated, precisely corresponding to the multi-information constraint, right? Because given Xn, those two, I put the upper bound on this, and this turns out to be useful in upper bounding. This basically somehow the upper bound on the multi-information basically puts some correlation constraint on Z bar and then Yn. And given this multi-information constraint, due to the transportation inequality, we can also control the distance between this Z bar n and Yn. And this distance between Z bar and the Y bar n eventually corresponds to, right? So the translates to our upper bound on the joint entropy of Z bar and Yn. And as we know, right, as long as we have a joint upper bound on the joint entropy of Z bar and Yn, which is actually smaller than the joint entropy of Z and Yn. So it turns out that this tighter upper bound on the joint entropy will allow us to, obtain the desired upper bound, which allows us to eventually solve Kohlberg's problem. So I think I'll just stop here and take any questions.
Thanks a lot.
Yeah, thank you, Salim.
So if anyone has questions, so the floor is open. If you can go ahead and ask your question. Maybe in the meantime, I can ask a quick question.
Sure. Yeah.
So I really like the talk. I like that there's the theory part and there's the application, and this is really nice.
Oh yeah, thank you. So I think there's a lot of other applications I unfortunately didn't get a chance to talk about. Some of them are our ongoing work, but I'm just thinking, this line of research is nice precisely because it's kind of easily adapted to our information theory people, because just like David make the comments, right? We information theory people wants to make some progress on machine learning community as well. And I think optimal transport is a very natural linkage between those two communities, information theory and machine learning. Yes.
And so do you consider that result to be surprising, that you need the capacity to be infinity to achieve the maximum, or what was your kind of
oh, this one.
Yeah.
It's indeed quite surprising. Basically, my personal takeaway is that if a problem has been open for more than 30 years, right? So it has to be like either way, makes some sense. But it's either way, it's kind of surprising. So in my personal takeaway, right? So originally I approached this problem actually, like many years ago. At that time, we were thinking about, really has to be able to do something, right? So at least reduce this zero from infinity to some finite number. But eventually, we guess that, it also makes sense because it somehow suggests that if I want to achieve the full capacity, right, at the full capacity rate to recover Xn, I have to be able to recover Zn as well. And it turns out that what we have shown is a Gaussian case. Turns out this result holds for the binary symmetric case as well. There's a following up paper also by 3 people. what we can show is that even the channel is replaced by binary symmetric relay channel, you have to basically use, in that case, you use the so-called sleeping for coding, right? By sleeping for coding, you transfer Zn to the Yn. You losslessly recover Zn. Only that you can recover message at the full capacity rate. So I guess it's surprising, yes or no? Yes, in the sense that, it makes sense to fully recover Zn to recover Xn at a full capacity. It's surprising in the sense that you cannot do anything smarter than that. Yeah. So
then, like, I don't know, in my mind, I'm thinking like, it seems like any error on the link C0, it's not going to be eaten up by the global error at Yn somehow.
Exactly. So another, actually, to make it even surprising, and we can do the following thought process, right? So a very interesting thought experiment, I think, is the following. Imagine those two n, let's say n1, n2 gets to very large, right? Extremely large. So that the full capacity is almost diminishing, is almost equal to 0, right? Yeah. In a very noisy regime, in a very, very low SNR regime, even the full capacity gets to 0, but you still need an infinite amount of link capacity to achieve a diminishing capacity overall. So in that sense, it's indeed surprising, I guess.
Or maybe another thought argument would be, suppose the C0 is noisy with noise variance or noise power going to 0, then how do you approach the capacity that you want to approach?
Say that again. If a C0 is close to 0, right? So this is very small.
Yeah, absolutely. I'm thinking it's not close to 0, but I add this, like, I'm thinking of it as a Gaussian also, but very low power.
Okay, got it. So you're saying kind of replace this digital link by Gaussian channel, sort of.
Yeah, but it's something that goes to 1 instead of like
So the thing is that if you replace this noiseless channel with a fixed capacity, replace that by a noisy channel, it's actually not difficult to show that they share the same capacity. Basically, what I'm saying is that if you replace this link, the pipes, by a same capacity, by a noisy channel with the same capacity, then those two problems will be the same. Yeah.
Okay, good.
Okay.
I don't know if there are other questions.
I just want to ask this question. So I'm not very familiar with the field, but like, does it make sense, for example, to formulate the problem in a way that I want to minimize the cost function, but actually I want to maximize the mutual information between the original space and the image space? Like,
okay, so what you ask, I guess, is a do question. If you fix the upper bound on the mutual information, minimize the cost.
I want to fix a lower bound on the mutual information. So I want to do this mapping that that show in Euclidean terms that they are really different. Like, I want to minimize this distance between them.
Yes.
But I want to keep as much information as I want.
Then it's 0, no? I think.
So there's a possible way to write out a do form, right? So it's just like you can. A linkage between optimal transport and the information theory I didn't get a chance to mention is that it's very close to the rate distortion form, right? Think about it as your distortion. Think of this as your rate. Mm-hmm. There's, of course, two ways to write up a rate distortion function. This is so-called distortion rate, right? You fix some rate constraint, minimize the distortion, but vice versa, you can do rate distortion, meaning that you fix distortion to be not exceeding some threshold, and you want to minimize the rate, right? So basically corresponding to the two ways to look at rate distortion function if you are coming from the information theory community. So there is a do form. Yes.
Okay, thank you.
Mm-hmm.
All right, thanks a lot, Xiugang.
Okay, thank you very much, Salem. Yeah,
yeah,
my pleasure to be here. Yeah. Thank you. Keep in touch. Bye.
Bye.
Mm-hmm.